This is my geometry course. Today we're going to learn coordinate proofs and bisector theorems. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. We're going to start with coordinate proofs. A coordinate proof is a proof that uses a graph, and we place a shape on the graph, in this case a triangle, and we position the vertices of the triangle at certain coordinates, and we use the coordinate system to prove characteristics about the particular shape. Again, in this case, the triangle. Now, I want you to understand that the coordinate proofs are very, very different from the two-column proofs that we learned in previous classes in this course. I'm not going to force you to do really formal coordinate proofs. I just want you to get the general idea, because coordinate proofs are really not a big part of the geometry curriculum. So I'm not going to take all the time to do a really formal proof. It says, show that the triangle below is isosceles. Now remember, an isosceles triangle is a triangle where two of the sides have equal length, or technically you might have an equilateral. That's isosceles too. That's not a perfect equilateral, but so what we have to do in this proof is we have to show that this length is equal to this length. You can see that this length is not going to be equal to the other ones because it's a little bit longer. And we're going to use the distance formula to show to find the distance between L and Q. And we're going to show that that distance is the same distance between L and M. Now I'm going to write the distance formula just in case you forgot it from the last class. x2 minus x1 squared plus y2 minus y1 squared. Now, if you want to, you can use the triangle method to find the distance between points. For example, if you wanted to find the distance between L and Q, you would draw this triangle and find the length of the legs. To find this leg, you would subtract the y values, that would be 1. And to find this leg, you subtract the x values, that would be 7. And then you just use a squared plus b squared equals c squared to find the distance. If you wanted to find the distance between L and M, you would use this triangle and subtract the x values, and you would have 1 here, and subtract the y values, and you'd have 7 here for that leg. And again, just use a squared plus b squared equals c squared. But in this class, we're going to use the distance formula. The first thing we're going to do is we're going to find the distance between L and Q. I'm going to make L 0.1 because that's the first letter in that subscript there, and Q 0.2. I'm not going to take the time to assign variables and all that type of stuff because that would just take too long. So we have 7 minus 0 squared plus 8 minus 7 squared. And I'm just going to kind of rush forward here because by now you should know how to do this. I don't need to show every step. And we have root 50. And if you want to pull out a perfect square, we have 5 times root 5. Now, if you don't remember how to pull out a perfect square, you can just go to my beginning algebra class that teaches how to do that. So now I'm going to write a squiggly line here, and we're now going to find the length between L and M. So we found the length between L and Q. Now we're going to find the length between L and M and show that it's the same length. So using the distance formula, I'm going to make L 0.1. So we have 1 minus 1 squared, or 1 minus 0 squared, and we have 0 minus 7 squared. And simplify that, and you can see we have root 1 plus 49, and we're just going to get the same thing we got before. So that would be root 50. And you don't really have to pull out a perfect square. All we're trying to do is show that they're equal, but might as well. So now you can see that those two lengths are equal. And so we proved that the triangle is an isosceles triangle. Now we have to make some sort of concluding statement. So we're going to say, therefore, triangle LQM, and remember there's 6 different ways to write the letters, you know, whichever way you want to use. LQM, triangle LQM is an isosceles triangle. All right, you can probably just say is isosceles, actually, just to save time. You can think of isosceles as an adjective. All right, so as you can see, it's not too bad. We're just using the distance formula. So now it's time for you to try one of those problems. I'm going to go ahead and leave number 1 in the window so you can see what's going on there. And try number 2. Use that distance formula. You have it there. I wrote it down. You can see in number 2, this side is not going to be equal in length because that's bigger. It's going to be these 2 sides that are going to be equal in length. So you want to find the length of TR and RP and show that they're the same length. So go ahead and try number 2. I'm going to leave number 1 in the window there. And when you come back, we'll do it together. All right, we're back. So first, we're going to find the distance between T and R. Doesn't really matter what order. And I'm going to make T 0.1. So we have 6 minus 4 squared plus 2 minus 8 squared. And we just simplify and we get root 4 plus 36. And we have root 40. And if you want, you can pull out a perfect square. It's not really that important in this class, but there you go. So the distance between T and R is 2 root 10. So if you got that answer, good job. Now we have to show the distance between, we have to find the distance between P and R. So distance between P and R, I'm making P 0.1. So we have 6 minus 0 squared, 2 minus 0 squared. And when we simplify that, we should get 2 root 10. So we have 36 plus 4. And you can see we're just getting the same thing. So we proved it. We proved that those lengths are equal. And so we need to make a final conclusion statement. Therefore, so if you didn't write this conclusion statement, be sure to do that. Triangle TRP is isosceles. And I'm just treating that isosceles word as an adjective. So if you got those answers, good job. So these are coordinate proofs, and as you can see, we're not really doing a very formal proof. We're just basically getting the general idea. And again, these proofs are not really a big part of the curriculum, so we're not going to spend a lot of time in this class doing these coordinate proofs, but I just want you to get an idea of how this works. And at the same time, you're applying your knowledge of the distance formula. And in this next problem, you're going to apply your knowledge of the midpoint, how to find the midpoint in 2 dimensions. So let's try number 3 together. It says, prove that the diagonals of the quadrilateral below bisect each other. So we have a quadrilateral here. That's a shape with 4 sides. And we want to show that the diagonals bisect each other. Now wait a second, what's a diagonal? We haven't talked about that yet in this course. These are the diagonals. It's when you take, you draw a segment from one vertex to another vertex. So that would be one diagonal, and this is another diagonal. That wasn't exactly straight, but you get the point. So we want to prove that those 2 diagonals bisect at the same point, because we want to show that they bisect each other. If they bisect, remember bisect means to kind of cut in half. So that means that this length has to be equal to this length, and this length has to be equal to this length. But if we can show that the midpoint of this segment and this segment, if we can show that that midpoint is the same for both of them, then just by the definition of midpoint, that proves that the two segments bisect each other. They cut each other in half. So this one cuts this one in half, and this one cuts this one in half. I know that's kind of confusing to think about, but that's basically what we're doing here. All you have to do is find the mid-segment of those diagonals. So let's write the midpoint formula there, if you forgot it from the last class. So that's how to find the midpoint. So we're first going to find the midpoint between H and F. The midpoint between H and F, you just plug in your x values and divide by 2, and that gives you the x value of the midpoint between H and F. And then plug in your y values. That'll be 1 plus 1. Divide by 2, that gives you your y value of the midpoint between H and F. So the midpoint, if we simplify, we get 1 and 1. So 1, 1. That seems about right. 1, 1's about there. It should be about the midpoint there. So now we're going to put a little squiggly line. We're going on to the next thing. We're now going to find the midpoint between E and G. So we're going to add the x values, divide by 2, add the y values, divide by 2, and the midpoint between E and G, if we simplify, I'm skipping a lot of steps here with the simplification, but I don't think you really need me to show every step if you did the homework and paid attention in the last class. So there you go. We showed that the midpoints of those diagonals have the same coordinate, which means they just cut each other in half based on the definition of a bisector. I didn't really give a lengthy explanation of that, but that's, it's just based on the definition of midpoint. It just cuts it in half. So they're bisecting each other. So therefore, the diagonals bisect each other. Remember, you always have to put a conclusion. Again, these proofs are a little informal, but we still have to have some sort of structure to them because the midpoints are the same coordinate, 1, 1. That works. So I'm going to leave that one in the window for you, and I want you to try number 4. So go ahead and attempt that problem, and when you come back, we'll do it together. All right, we're back. So first, let's find the midpoint between D and B. Doesn't really matter which order we use. 6 plus 8 over 2. 5 plus 3 over 2. And we just have to simplify that. And we get 7 and 4. Again, I kind of skipped forward a little there. Now we're going to find the midpoint between A and C. And we have 4 plus 10 over 2 and 7 plus 1 over 2. And if we simplify those, we get 7 and 4, which is the same point, which proves that the diagonals bisect each other. So we can say, therefore, the diagonals bisect each other. So if you got those answers, good job. Remember, you have to write that final statement. If you didn't do that, write that conclusion statement. All right, so we use the distance formula in the first 2 coordinate proofs, and we use the midpoint formula in the second 2 proofs. Now we're going to go on to parallelograms. We did coordinate proofs of triangles. We did coordinate proofs with quadrilaterals, and I guess those were probably parallelograms, but now we're going to go do some more parallelograms. But before we do this next proof, we're going to have to talk about a few things. Says show that the quadrilateral is a parallelogram. So we have to prove that this is a parallelogram. We can't do that because we don't know what a parallelogram is. We haven't defined what a parallelogram is in this course yet. So that definition is up here. A parallelogram is a quadrilateral, meaning a shape with four sides. A quadrilateral with two pairs of parallel sides. So let me show you what that means. This is a pair of parallel sides, and this is a pair of parallel sides. Now you might be thinking, what is parallel? What does that mean? Well, we talked about it in my previous course. That just means that they're lines that are they're not going to touch each other. See, if I draw two lines like this, they're eventually going to touch each other. But if I draw them so that they're going kind of in the same direction, they're never going to cross. Those are parallel lines. So these lines, these line segments, if you extended them out, they would never cross. AD would never cross with BC, so they're parallel. And AB would never cross with DC, so they're parallel. So we have to show that this quadrilateral has two pairs of parallel sides. Now, how do we do that? How do we show that they're parallel? Well, what we're going to do is we're going to measure the slopes, and we're going to show that the slope of this line segment is equal to the slope of this line segment. And the slope of this line segment is equal to the slope of this line segment. But what is slope? What is that? Well, if you took the prerequisite for this course, my beginning algebra course, you know, or you may recognize that word. Slope just measures the steepness of a line. So if a slope is a large number, the line may be going up. It may be very steep. If it's a fraction, a positive fraction, it might be very shallow. If the slope is negative, it's going down. And if it's zero, the slope is zero, the line is flat. And if the slope is undefined, it's vertical. So the slope measures the steepness. Now, if two line segments have the same slope, that means they're parallel. So all we have to do in this problem is just find the slopes of those line segments. All right, so how do we do that? Well, again, in my previous class, we learned the slope formula. This is the slope formula. So if you want, you can go ahead and get a screenshot of all those principles here, that review. So if I want to find the slope between, say, 2, 3, and -4, 0, then I just plug it into this slope formula. Now I have to assign letters. So I'm making this point 1 and this point 2, and then you just plug in. So the slope, which is usually notated with a lowercase m, is equal to 0 minus 3 over -4 minus 2. And simplify, you get -3 over -6, which is positive 1/2. So that's how you find the slope. And so that's what we're going to do here. All right, so we're going to look at, again, we have to show that two pairs of sides are parallel. So I'm going to find the slope of line segment AB. And I'm not going to assign letters to each point. I'm just going to say that A is 0.1. So we would do 8 minus, let me write that formula up there. Again, you should get a screenshot of that, but I'm just going to let you know what formula I'm using. So 8 minus 5 over 2 minus -1. And the slope of line segment AB, if you simplify, you get 3 over 2 plus 1, which is 3. And we get, I'll make sure I have enough room here. I'm just going to write 1 over here. You're allowed to go to the right. So that's the first slope we found there. Now we're going to find the slope of the opposite side. The opposite side of AB is DC. So I'm going to find the slope of DC, and it should be the same. It should be the same slope if they're parallel. So I'm going to let C be the second point. So that would be 4 minus 1 over 4 minus 1. And that gives us 3 over 3, which is 1. So we got the same slope. So that proves that those line segments are parallel. So now I'm going to find the slope of side AD and show that that slope is the same as side BC. So using A as 0.1, I have 1 minus 5 over 1 minus negative 1. And that gives us negative 4 over 2, which is negative 2. All right, so now we're going to find the slope of the opposite side, which is BC. Using B as 0.1, I have 4 minus 8 over 4 minus 2. And we have negative 4 over 2, which is negative 2. So you can see that those slopes, let me get a different color here, those slopes are both the same. So that proves that side AD is parallel to side BC. So we've shown that we have two pairs of parallel sides, a pair here and a pair here. So we can conclude, therefore, the quadrilateral is a parallelogram. And we're done. So it's not too bad. It's a little harder than the first two problems we did, but it's not so bad. So you can get a screenshot of this if you want. You're going to do a problem like that on your own. You can refer back to that if you need to. So for number 6, show that the quadrilateral is a parallelogram. So you're going to show that this side is parallel to this side, and this side is parallel to this side. Now just be aware, this is a flat line, so the slope of that one is going to be probably 0. So go ahead and try number 6, and when you come back, we'll do it together. All right, we're back. We're going to find the slope of side, I guess we'll just stick with AB. Using A as the first point, we have negative 2 minus 5 over negative 9 minus negative 7, negative 9 minus negative 7. And we have negative 7 over negative 2, which simplifies to 7 over 2. I guess I can just go down there so it's not so cramped. All right, so that is the slope of AB. Now we're going to find the slope of the opposite side, which is DC, and they should be the same. Using D as the first point, we have negative 2 minus 5. And 4 minus 6. Simplify, we get negative 7 over negative 2, which simplifies to positive 7 over 2. And you can see that we have the same slope on both of those. So those two line segments, those sides, are parallel. So now we move on. We've shown that one pair of sides of the quadrilateral are parallel. So now we're going to move on to the other pair. We'll find the slope of AD. And using A as the first point, we have 5 minus 5 over 6 minus negative 7. That would be 0 over 13, which is just 0. So when we find the slope of the opposite side, which is BC, that slope should also be 0. Using B as the first point, we have a negative 2 minus negative 2. Over 4 minus negative 9. And that would be negative 2 plus 2. Remember, these become these become positive, these two negatives, because that's a double negative. So it would be negative 2 plus 2 is 0. And that would be 13, and we have 0. So you can see that those slopes are the same, proving that the that pair of sides are parallel. So we have two pairs of sides that are parallel. We have one pair here, and we have one pair here, and that proves that the quadrilateral, therefore the quadrilateral is a parallelogram. So if you got that answer, good job. All right, on to number 7. So this is the most difficult one of these types of problems we're going to do, because this is going to require the most work, but don't worry, we'll get through it quick. We're going to show we did triangles and we did parallelograms. Now we're going to do a problem with a square. So we have to show that this quadrilateral is a square. We can't do that because we don't know what a square is. I mean, we can probably recognize a square, but what's the exact definition? Well, a square is a quadrilateral with all sides congruent and all angle measures 90 degrees. So we have to show that all these sides have the same length. All of them, all 4 of them have the same length. And we also have to show that all the angles, this angle, this angle, this angle, this angle, we have to show that they're all 90 degrees. So I just assume that they're 90, and I drew a box there, but we don't know that they're 90, you see. We just know that they're angles. We don't know if they're 90. We have to show that they're all, the measures of the angles are all 90 degrees. All right, so we're first going to find the distance between the points A and B. I'm using A as the first point. So we have 3 minus negative 3 squared. And we have 5 minus 3 squared. And again, just rushing forward here, we have 6 squared is 36, and 2 squared is 4. All that simplifies to root 40. And 40 is 4 times 10. 4 comes out as a 2, and we have 2 root 10. So we found the distance between A and B. Now we're going to find the distance between B and E. It doesn't really matter what order you do this in. Using B as the first point, we have 5 minus 3 squared, and negative 1 minus 5 squared. And again, just rushing forward here, we have 4 plus 36, which is root 40, and we can simplify that to 2 root 10. And I should probably just go to the right there to save room, because we got a lot of work to do here. I don't want to run out of room. All right, so you can see that those lengths are equal. So we have 2 more sides to find the lengths of. So we're going to find the length between points A and C. Using A as point 1, we have negative 1 minus negative 3 squared, and negative 3 minus 3 squared. And simplifying, we have 4 plus 36, which is expected, root 40, which equals 2 root 10. It's not really necessary to pull out the perfect square. We're just trying to show that they're equal, but I just want you to get that habit. Now we're going to find the distance between C and E, and this is the last distance. We just have to show that it's 2 root 10, And then that first part of the definition of a square will be done. We'll have shown that all the lengths are equal. So using C as point 1, we have 5 minus negative 1. And negative 1 minus negative 3. And simplifying there, we have root 36 plus 4, which simplifies to 2 root 10. And you can see all the side lengths are equal. So we've shown that all the side lengths are equal, but that's not enough. We also have to show that all the angle measures are 90 degrees. Because there are quadrilaterals where all side lengths are equal, but they're not squares. Their inner angles are not all 90 degrees. You're going to find that as we go into other parts of this course. So now we have to show that all the angle measures are 90 degrees. How do we do that? We haven't learned how to do that in this course yet. So what we're going to do is we're going to use this principle, if I can find it, this principle here, slopes of perpendicular line segments. If the slopes of two line segments are opposite reciprocals, then the measure of the angle between the line segments is 90 degrees. Now, what in the world does that mean? Well, let me show you. Let's say that you have the number, let's say 7/8. The opposite reciprocal, you flip it and change the sign. So opposite, meaning you change the signs. It goes from positive to negative. And reciprocal, meaning you flip. All right, so let me give you another example. Let's say you start out with a negative 3/4. What would the opposite reciprocal be? Well, it would be positive 4/3. If you said 4/3, you're right. Now, there are some tricky situations. For example, you might get something like a whole number. How do you deal with that? Well, you just pretend that it's over 1. Remember, you can write any whole number as over 1. And then when you flip it, you just change the sign and it becomes negative 1/8. All right, so that's what we're going to do. So those are opposite reciprocals. So if you have two line segments and their slopes are opposite reciprocals, that proves that this angle is 90 degrees. So again, if you don't understand all that, that's okay. We're going to do some problems here, and you're going to see exactly what we're talking about. So now we're going to move on to the slopes. So we will find the slope of AB. So just to remind you, now we're using this formula. Let me show you the formula. y2 minus y1 over x2 minus x1. So we're changing formulas now, okay? We're not doing the distance formula. We're using this formula. So again, get a screenshot of that. This formula here. The slope formula and the distance formula, they have some similarities you may have noticed, but they are quite different. So the slope, I'm going to get rid of this because I don't really have room to show that. The slope of line segment AB, using A as point 1, we have 3, actually it's a 5 minus 3 over 3 minus negative 3. And that would be 2 over 6, which is 1/3, if you reduce it. So now let's find the slope of BE. All right, the slope of BE should be the negative reciprocal, because that's a side that's right next to it. So we want these sides to have slopes that are negative reciprocals, because that proves that this angle is 90. So BE, we found AB. AB was 1/3. This is 1/3 right here. We want this to be negative 3, because that's the opposite reciprocal. So using B as point 1, we have negative 1 minus 5 and 5 minus 3. So we get negative 6 over 2, which is negative 3. So these are opposite reciprocals. See, if you flip this and change the sign, you get negative 3 over 1, which is the same thing as negative 3. So we proved, by doing that, we proved that this angle is 90 degrees. Now, if I find the slope of this line segment, remember, I already found the slope of this line segment, so if I find the slope of this line segment, that'll prove that this angle is 90 degrees. So we're going to find the slope of line, our length AC. So slope of AC, using A as 0.1, I have negative 3 minus 3 over negative 1 minus negative 3. And that gives us negative 6 over 2, which is negative 3. So these two, we just proved that these two line segments, AB and AC, are perpendicular. That's another way to describe it. Perpendicular. The definition of perpendicular is 90 degrees. So if these two line segments are perpendicular, that means that this angle is 90 degrees. I don't know if I mentioned that. I should have mentioned that. So we showed that that angle is 90. So let me just recap what we've done here. We've shown that this angle is 90, and we've shown that this angle is 90. Now, all we have to do to show that these two angles are 90 is to find the last slope. So we're going to find the slope of segment CE. So slope of CE, using C as the first point, we have negative 1 minus negative 3 over 5 minus negative 1. 5 minus negative 1. And we have 2 over 6, which is 1/3. And that's what we expect. So let me try to buy some room here. I should section these off so we can utilize a little more room. So all those slopes prove that the angles are all 90 degrees. So now we have to make a conclusion. Remember, you have to make a conclusion for these proofs. You can say, therefore, the quadrilateral is a square. So I know that was kind of a lot of work, but you just have to do one of these and then we can go on to something else. So go ahead and take a screenshot of that if you need it. And I want you to try a problem like that. I want you to try number 8. Show that the quadrilateral is a square. Again, we have to show that the lengths are all the same by using the distance formula, and we have to show that the slopes of adjacent sides are perpendicular, meaning the angle measures are 90 degrees for all vertices. So go ahead and try number 8, and when you come back, we'll do it together. All right, we're back. So we're going to find the distance between E and G. It doesn't really matter what order you do it. Using E as 0.1, we have 3 minus 2 squared plus 5 minus 2 squared. That simplifies to 1 plus 9, which is root 10. So we have root 10 there. That's the distance between E and G. Now we're going to find the distance between G and H. Again, it doesn't matter what order you do this in. Using G as the 0.1, we have 6 minus 3 squared plus 4 minus 5 squared and we have, rushing forward, we have 9 plus 1, which is root 10. And so we've shown that those two lengths, those two sides, are equal in length. Now we're going to find the distance between h and f, just going around the square there. Using h as 0.1, we have 5 minus 6 squared plus 1 minus 4 squared. And rushing forward, that simplifies to 1 plus 9, which is root 10. So we've almost shown that all sides are equal in length. Now we have to find the distance between EF, or distance between E and F. So that would be, using E as 0.1, we have 5 minus 2 squared plus 1 minus 2 squared. And we have root 9 plus 1, which is root 10. So you can see, you can see all side lengths are equal. Now we just have to show that the angle between all the sides, the inner angles, are all 90 degrees. So 90 degrees, 90 degrees, we have to show that all of them are 90. So we're going to use slopes to do that. So let's try the slope. Let's try to do it in the same, well, let's try EG. We're going to find the slope between, or the slope of the line segment EG. So that is, using E as 0.1, we have 5 minus 2 over 3 minus 2, which is 3 over 1, which just simplifies to 3. So that's the slope of EG. Now the slope of GH should be the opposite reciprocal. Using G as 0.1, we have 4 minus 5 over 6 minus 3, and then we get negative 1 over 3. That's the opposite reciprocal of 3. So that proves that one angle is 90. Now we just have to find the other slopes. 3, negative 1/3. So now we've shown that, let's see here, GH, EG. So we've shown that this angle is 90 and this angle is 90. We just have to find one more slope to show that this angle is 90 and this angle is 90. So the slope of FH, using F as 0.1, we have 4 minus 1 over 6 minus 5, which equals 3 over 1, which is just 3. And that is the negative reciprocal of these other two. So really you just have to prove that two slopes are the same and the other two slopes are opposite reciprocals, sometimes called negative reciprocal. All right, so we can just write a conclusion statement. Let's section these off first. The conclusion is, therefore, the quadrilateral is a square. So if you got those answers, good job. Remember, you got to write that conclusion statement. All right. So I know that those square problems are a little difficult, but we're not going to do any more of those today, so don't worry about that. All right, now we're going to learn something called the Midsegment Theorem. Now, we can't learn the Midsegment Theorem unless we first learn what a triangle midsegment is. A triangle midsegment is a segment that connects, it's a segment that connects the midpoints of two sides of a triangle. So this is a midsegment, this orange line down here. This orange line here is a midsegment. It connects, this is the midpoint of AB, side AB, and this is the midpoint of side BC. And remember what midpoint means, that that just means it bisects the side. It cuts it in half, so this length is the same as this length. And this green dot here, that midpoint, it makes it to where this length is equal to this length. That's just the definition of midpoint. So this segment here connects those two midpoints. So that is the triangle midsegment. Now it might be relevant to understand that there's actually three midsegments in each triangle. So I can draw a midsegment here, and I can also draw a midsegment here. And so we're just showing one midsegment. So now that we know what a midsegment is, we can learn the midsegment theorem. The midsegment theorem says the midsegment of a triangle is half the length of the non-included side and also parallel to the non-included side. So there's actually two things that this is saying. Number one, it's saying this length is half of this length. This is the non-included side because it doesn't. The midsegment doesn't touch that side. It touches this side and this side, but it doesn't touch the non-included side. That's why I'm calling it non-included. So this length, the length of the midsegment, is half the length of the non-included side. But the theorem says two things. It also says that this midsegment has to be parallel to the non-included side. So you may want to get a screenshot of this information. And now we're just going to do some basic problems to make sure that you understand exactly what the midsegment is saying. It says if AB is a midsegment of each triangle below, find X. So we know that AB is a midsegment. So the midsegment theorem tells us that if AB is a midsegment, it must be half the length of the non-included side. So the length of X must be equal to 5 centimeters. So as you can see, that's pretty easy. There's no tricks there. So we have the same situation on number 10. This length is half of the non-included length. So that means that this side must be 6. It must be double. So we can say 2x minus 3 is equal to double 3 meters. So 2x minus 3 is equal to 6, and that's a two-step equation. Add 3 to both sides, and long story short, you get 9/2. So the answer to that one is 9/2. We found x. All right, on number 11, this is kind of a twist problem on number 11. If AB is a midsegment, that means that by definition, this length must be equal to this length. So if we're looking for x, x just must be this 100 inches. X is 100 inches. So don't be fooled by those types of problems. We didn't really even need the midsegment theorem. We just needed to know that AB was a midsegment because by definition, x must be 100. So be aware that you may encounter some of those problems. Now, I didn't mention, I just want you to be aware the midsegment theorem is not really that important of a theorem. It's not a big part of the geometry curriculum, but you may see it, so we do have to learn it. All right, so time for you to try some problems. If you didn't get a screenshot of that, go ahead and get a screenshot of that theorem. Try number 12, and when you come back, we'll do it together. Remember, this length is half of this length. Find x. When you come back, we'll do it together. All right, we're back. So x minus 10, because 26 is half of the length of the non-included side, we have to multiply 26 by 2, because this length must be double the midsegment length. So then we get 52, and just add 10 to both sides, and we have 62. X is equal to 62. So if you got that answer, good job. Number 13, go ahead and try number 13. And when you come back, we'll do it together. I just want to give you a clue. In number 13, you don't actually need the midsegment theorem. All you need to know is that AB is a midsegment. Go ahead and try 13, and when you come back, we'll do it together. All right, we're back. X is equal to 2 meters. Why is that? Well, because we're told that AB is a midsegment. So that means it must cut this side in half. And so if this length is 2, this length must be 2 also. So if you got that answer, good job. Try number 14. You will need the midsegment theorem in number 14. And when you come back, we'll do it together. All right, we're back. The midsegment theorem tells us that x, the length of the midsegment, must be half the length of the non-included side. So 6.8 divided by 2. Therefore, x is 3.4 millimeters. You may have needed a calculator for that. That's okay. All right, so now on to a little more challenging problems. So to number 15, we're supposed to find x. I want you to notice that there are actually 3 triangles here. There's this triangle, there's this triangle, and there's the big triangle, the biggest triangle. Now, we can use these lengths. We know that this segment here, that 1.9 meter segment, we know that that's a midsegment of this triangle. How do we know that? They didn't tell us it's a midsegment, so how do we know that? Well, we know it just because this length is 2 and this length is 2, so we know that this segment bisects this length. And we know that this length is 3 and this length is 3, so that means that this segment also bisects this length. So that means that this segment here is a midsegment. If it's a midsegment, that means that this length must be double this length. So this length must be, I'm going to write it in red, this length must be 2 times 1.9. 2 times, I don't really have enough room, I'll just do that, it would be 3.8 centimeters. And now, if we analyze further, we can see that this length, which is 2 plus 2, do you see why that length is 2 plus 2? This length is 4, and this length is 4. So that means that this segment bisects this length. And this length is 3 plus 3, which is 6. And this length is 6. So those lengths are equal, which means that this length also bisects this side. I know that's kind of complicated. But we're now looking at the biggest triangle, and we're saying that this is a midsegment of the biggest triangle because of these lengths. So what that means is that this length here must be double this length. Or you can say this length is half of this length, however you want to say it. So now we have to double 3.8. So x over 2 is equal to 2 times 3.8. And 2 times 3.8 would be 7.6. And then we just multiply both sides by 2, and we get x is equal to 15.2. So the answer is 15.2. So I know that seems kind of complicated, but hopefully you got the basic point there. It's kind of a challenge problem. So try number 16, and when you come back, we'll do it together. All right, we're back. Now for this problem, we have to start with the bigger triangle, because we don't have this midsegment here, or this midsegment. Now we know that this length is 20, and this length is also 20 if you add those 10s together. This length is 14, and this length is also 14 if you add those 7s together. So that means that this is a midsegment, which means it's half the length of 32, half the length of the non-included side. So this side would be 16 kilometers, that's half of 32. And we also know that this is a midsegment, this x length here, because we have 10 and 10, so that cuts that side in half, and 7 and 7. So this is a midsegment also, which means it must be half the length of the non-included side. So that means x is 8 kilometers. So if you got that answer, good job. That was kind of a challenge problem. If you didn't get it, that's okay. You can go back and figure out how to do that. All right, on to number 17. So now we're going to show that the midsegment is true for specific cases, for specific triangles. In this case, we have this triangle here. And this is just going to help us remember what the midsegment theorem says, and it's also going to help us review how to use the distance formula and the midpoint formula and the slope and so on and so forth. So we're going to show that the midsegment connecting CA and AB, so that would be a midsegment that looks something like this. Remember, there's 3 midsegments for each triangle. You have one here, and one here. We're looking at a particular midsegment, the one that connects CA and AB. So that would be something like this. We're going to show that this length is half the length of CB and parallel to CB also. So these two are going to be parallel. So we're showing that the midsegment is true. The midsegment theorem for this particular triangle is true. So we have to let's start with finding the lengths between the lengths of the midsegment and the lengths of the non-included side, or length of the non-included side. We can't find the length of the midsegment because we don't have the midsegment. We don't know, we don't have any points on the midsegment. But to find the points on the midsegment, all we have to do is find the midpoint between A and C, which would be somewhere around here, and we find the midpoint of A and B, and then just use those two coordinates to find the distance with the distance formula, or the length of the midsegment with the distance formula, and then we can find the slope using those 2 points and show that slope is equal to the slope of segment CB, which will prove that the midsegment is parallel to the non-included side. All right, so we're going to find the midpoint between C and A. So using our midpoint formula, we're going to add -5 and 1, divide by 2, and we're going to add -1 and 3, divide by 2, and we get -2 and 1. So that's the midpoint of CA. So -2 and 1 would be about exactly there. All right. So now we're going to find the midpoint of A and B. So midpoint of AB is add the x values, 3 plus 1 over 2, and add the y values, 3 plus -1, divide by 2, and the midpoint is going to be 2 and 1. So 2 and 1 would be about there. So that's what we'd expect. So now we have 2 points that we can use to find the length of the midpoint. So we have this point and we have this point, and we're going to find that length to show that this length, that length there, is half of this length by using the distance formula. But again, we couldn't do anything until we had those midpoints. So now we're going to find the distance, and I'm just going to write dm, distance of the midsegment, distance or length of the midsegment, and we're going to plug in those numbers, and I'm going to make this point 2, so that would be 2 minus -2 squared plus 1 minus 1 squared, and that gives us root 16 plus 0, which gives us root 16, which is 4. So that length is 4. So now we have to find the distance between C and B and show that that is double that distance. So it should be 8 if the midsegment theorem holds for this particular problem. So using C as 0.1, we have 3 minus -5. And -1 minus -1. And simplifying, we have root 64 plus 0, which simplifies to root 64, which is 8. So you can see that that length is double. So we proved the non-included side is double the side, or double the midsegment length. So now all we have to do is prove that the midsegment is parallel to the non-included side. So now let's find the slope, which is usually notated with a lowercase m. We're going to find the slope of the midsegment. So I'm just going to write MID for midsegment. Slope of the midsegment. We have to use these 2 points here. So slope of the midsegment is going to be, I'm going to make this point 2. So that would be 1 minus 1 over 2 minus negative 2. And we get 0 over 4, which is 0. So now we're going to find the slope of segment CB and show that that's also 0. That'll prove that those two segments are parallel. So I'm going to use make C 0.1, and we have -1 minus -1 over 3 minus -5. And we have 0 over 8, which is 0. So we prove that they're parallel. So we can say, therefore, the midsegment theorem holds. So holds just means that it works for that particular case. Again, we don't have to be too formal here. All right, let's try another one of those together before you try one on your own. We have the same situation here. Show that the midsegment connecting CA and AB is half the length of CB and parallel to CB as well. So the midsegment connecting CA and AB. So it's a little bit different. So in this case, we're looking for this midsegment. Again, there's 3 midsegments for every triangle, but we want the one connecting AC and AB. So that's something like this. We want to show that that length is half the length of the non-included side and parallel to the non-included side. But we can't do anything with this midsegment because we don't have any points that we can use to analyze it. But all we have to do is just find the midpoint here and the midpoint here, and we can use that those points to find the distance, the length of the midsegment, and to find the slope of the midsegment, so we can compare it to the slope of the non-included side and show that they're parallel. So first, let's find the midpoint between A and B. We're just using the midpoint formula. So the midpoint between A and B is 1 and 3. So now we're going to find the midpoint between A and C. Again, just using the midpoint formula that we learned in a previous class. And the midpoint between A and C is -2 and 1. So what we did is we found this point here, 1, 3, that would be about here. And we found the other midpoint is -2, 1, which would be about here. So that makes sense. So now we're going to find the distance between those 2 points. And that is going to help us prove the midsegment theorem. So the distance, I'm just going to write dm, distance between the midsegments, or distance of the midsegment. I'm just going to write mid, I guess, equals, using these 2 points here, making AC 0.2, we have -2 minus 1 squared plus 1 minus 3 squared. And just doing the math there, we have 9 plus 4, which is root 13. So if that side is root 13, if that midsegment is root 13, this length here, this length here is root 13, this length should be 2 times root 13 because it should be double. So now we're going to find the length of the non-included side, so the distance between C and B, making C 0.1. We have 5 minus -1. Four minus 0. And we have root 36 plus 16. Add those up and you get 52. So we have root 52. Now this is where it's going to take a little doing here. We're going to have to factor 52. If you use your calculator, you divide it by 4, you find it 4 goes into it, so it becomes 4 times 13. And then we can use our basic root properties that we learned in the previous course, beginning algebra, and we get 2 root 13. So you can see it's exactly double the length of the midsegment, and that proves that that the midsegment theorem holds, or at least that part of it. So now we have to prove that this length, the non-included side, is parallel to this length. So we have to find the slope of the midsegment and the slope of CB. So first let's find the slope of the midsegment, and I'm just going to notate it as mid. So now we're using these 2 points. Using AC is 0.2, we have 1 minus 3 over -2 minus 1. And that is -2 over -3, which simplifies to 2/3. So that's the slope of the midsegment. Now when we find the slope of the non-included side CB, that should be also 2/3. So using C as 0.1, we have 4 minus 0 over 5 minus -1. And we have 4 over 6, which simplifies to 2/3. And you can see the slopes are the same, which proves that those sides are parallel. All right, so we can say, therefore, the midsegment theorem holds. Again, that's an informal way of saying that it works for this particular case. All right, so now it's time for you to try. I'm going to leave number 18 in the window there. Again, all we're doing is just showing that the midsegment theorem is true for these particular cases using our distance formula, midpoint formula, and our knowledge of what the midsegment is of a triangle. So go ahead and try number 19, and when you come back, we'll do it together. All right, we're back. So first we're going to find the midpoint of let's see, FE and QE. So we're going to find the midpoint of FE. And that is 1 and -1. Now we're going to find the midpoint of QE. And that is, there's the x value. And we have 5 and 2. So we have those midpoints. So be aware that this is counting in 8. You see, so each unit is 2. 5, 2 is 1, 2, 3, 4, 5, and 2. That would be about here. Looks like it would be about there. And the midpoint for FE, 1, -1, so that would be about here. So that's the midsegment. We have to find the length between those, or the distance between those 2 points. That's the length of the midsegment. So the distance, or length of the midsegment, is equal to, and we're using these 2 points. I'm going to use QE as 0.2. So we have 5 minus 1 squared plus 2 minus -1 squared. And just simplifying, we have 16 plus 9, which would be root 25, which is 5. So that's the distance of the midsegment. Now we have to show that the non-included side, which is FQ, we have to show that that's twice that distance, so it should be 10. So distance between F and Q, using F as 0.1, we have 2 minus -6 squared plus 8 minus 2 squared, and simplifying we get root 64 plus 36, which equals root 100, which then equals 10. So you can see that that's double. That's double the midsegment length. So we showed that the midsegment theorem holds for this particular example, for at least when it comes to that characteristic. We need to show that they're parallel also. We need to show that this midsegment, wherever it is parallel to this side. So we're going to find the slope of the midsegment. Slope of the midsegment using this point and this point. I'm going to use QE as 0.2, so that would be 2 minus -1 over 5 minus 1, which is 3 over 4. So now the slope of FQ must also be 3/4 if they're parallel. So I'm using F as 0.1, and we have 8 minus 2 over 2 minus -6, which equals 6 over 8, which is 3/4. So they are the same, and they are parallel. So we have to use state our conclusion, because this is a proof. So we say, therefore, the midsegment theorem holds. So if you got that answer, good job. All right, on to number 20. I want you to try one more of those problems. Again, the purpose of this is to learn the midsegment theorem and also learn coordinate proofs, and also review our distance formula and our midpoint formula. So let's go ahead and try number 20. And remember, each box is 2 units. So try number 20, and when you come back, we'll do it together. All right, we're back. So show the FQ and FE. FQ and FE. So that would be this midsegment. It's going to look something like that. We're going to show that midsegment length is half this midsegment length, and that they're parallel also. But we can't do that because we don't have a midpoint. We have to find this midpoint and this midpoint, so we can use those points to find the length and the slope. So we're going to find the midpoint between F and E. Actually, let's do F and Q first. So that would be 4 plus -8 over 2, and 4 plus 2 over 2. Simplify that, and we get -2. and 3. So now we're going to find the midpoint between F and E. So again, just to be sure, what we just did there, we found the midsegment, or the midpoint between F and Q, so that is right here. And now we're finding the midpoint between F and E, which would be somewhere around here. -8 plus 8 is over 2, and 2 plus -4 over 2. And so we get 0 and -1. So now we have those two midpoints. And now we have to find the distance between those midpoints. That'll give us the length of the midsegment. So I'm going to use, we're using these 2 points. I'm going to use FE as 0.2. So we have 0 minus -2. Plus -1 minus 3 squared, and just simplify those, and we get 4 plus 16, and simplifying that we have root 20, which becomes 2 root 5, pulling out a perfect square. So that's the distance. That's the length of the midsegment. So now we have to prove that the length of QE is double that. So it should be 4 root 5, not just 2 root 5. So we're going to find the distance between Q and E. Letting Q be the first point, we have 8 minus 4 squared plus -4 minus 4 squared. Doing all the math on that, we have root 16 plus 64, and 16 plus 64 is 80. Now 80 is 5 times 16, you see. You can factor it in many different ways. Again, you can go back to my beginning algebra course if you're having trouble factoring or taking out a perfect square out of those roots. But we can factor 80 in many different ways, but I want to factor it as 15 times 16. Or excuse me, 5 times 16, because that just makes it easier to pull out the perfect square. And we have 4 root 5. I'm not showing every step, but again, we've shown that the non-included side is, its length is double the length of the midsegment. All right, so now we just have to show that that QE is parallel to the midsegment. So I'm going to find the slope of the midsegment using these 2 points up here. Using FE as the 0.2, we have -1 minus 3 over 0 minus -2, and we get -4 over 2, which is -2. Now we're going to find the slope of QE. Letting Q be 0.1, we have -4 minus 4 over 8 minus 4, and we get -8 over 4, which is -2. So it's the same slope. That proves that those sides are parallel. So the midsegment theorem holds for this particular example. Again, we haven't done a proof to show that the midsegment theorem works in every case, but we're just showing that it works in these cases. We don't usually prove theorems in this course, or in most math courses they don't prove any theorems. They just you just memorize it. You're not really required to do anything else in most courses. So now we can say, therefore, the midsegment theorem holds. So if you got those answers, good job. So now we're going to go into coordinate proofs with variables. In the previous examples, we showed that the midsegment theorem worked for specific triangles, but now we're going to show that the midsegment theorem works for all triangles, because we've positioned the triangle here in a particular way. We put one vertex at the origin that's going to make things easy for us, and we have h, k, and m, which can be any numbers. So because they can be any numbers, this is going to prove that the midsegment theorem works for all triangles. And I went ahead and labeled one midpoint F and the other midpoint E. That's just going to help us. So it says here, again, write a coordinate proof to show that the midsegment theorem is true. So we're going to do the same thing we did before, just with variables now. So we have to find the coordinates of F and E. Then we're going to find the length between F and E. And we're going to show that that length is half of the length of the non-included side. And we're also going to show that this segment is parallel to the non-included side. So first, let's find the coordinates of F and E. That's the first thing we need to do. So we need to find F, which is going to be, add the x values of A and B. So that would be 0 plus h. I'll move it down a little bit. 0 plus h over 2. And again, it's really important to understand that you always want to position your polygon so that one of the vertices is at the origin. It just makes things easy for us. And the y value is 0 plus k over 2. And so now we see that the midpoint is h over 2 and k over 2. That's the coordinates of F. So now we're going to find the coordinates of E. So this is the midpoint between B and C, so we're adding h and m divided by 2. That's the x value, and k plus 0 divided by 2. So again, that 0 makes things easy for us. That's why we're positioning this vertex on the x-axis, because the y value is 0 and we just have less variables that way. I'm going to move this down a little bit. So now we just simplify that and we get the coordinate h plus m over 2 and the coordinate k over 2. So those are the coordinates of the midpoints. That's where the midsegment is going to, those 2 points are on the midsegment. So now we have to find the length of the midsegment using those 2 points that we just found. So we're going to find the distance between F and E. So I'm going to make F 0.1 because it comes first in this. So we have h plus m over 2 minus h over 2 squared. And we're going to have to make that root a little bigger. Plus k over 2 minus k over 2 squared. Now, we have good news and we have bad news here. The good news is this just cancels out. K over 2 minus k over 2, that's 0. But this here, that's going to require some algebra that we learned in my beginning algebra course. And so it's not too bad. I mean, we have a common denominator, so we can go ahead and just subtract the numerators. So what is h plus m minus h? Well, that's pretty easy. The h's just cancel out. You end up with m over 2, you see. So it's not too bad. But students really don't like seeing that type of stuff. Anyway, we have m over 2 squared plus 0 squared. Now this is the part where students are really going to get angry. They're going to think, I've never seen this before, but I don't know if we went over that a lot. We'll probably go over this more in the intermediate algebra course, but this is really easy. It's just m over 2 times m over 2. Now that we have learned quite a bit. We learned that in my pre-algebra course. So you just multiply, when you multiply fractions, you just multiply straight across. And m times m is m squared, and 2 times 2 is 4. So m over 2 squared is just m squared over 4. And we don't have to write that 0 because that would just be 0 squared is just 0. So now we're left with the root of m squared over 4. And now we learned in my beginning algebra course that square root of a over b is equal to square root a over square root b. So we have square root m squared over square root 4. And the square root of m squared, remember the square root is the opposite of squaring, so that just becomes m. And the square root of 4 is 2. Now I know what you're thinking. You're thinking, that's too complicated. I don't know how to do a lot of stuff. Well, the problems I'm going to give you in the homework are not going to be this difficult, so don't worry about it. The problems I'm giving you in the homework are very simple problems. This is just an example of a coordinate proof where you prove the midsegment theorem. So we found the distance between F and E is m over 2. So that's this distance here. The length of the midsegment is m over 2. And I should probably put dividers here. So now we're going to find the length of AC, the distance between points A and C, using A as point 1. We have m minus 0 squared plus 0 minus 0 squared. So this is going to be really easy. M minus 0 is just m, and 0 minus 0 is 0. So we have root m squared, which simplifies to m. Do you see why that is? Root m squared simplifies to m because it's just the rooting is the opposite of squaring, so you just end up with m. We talked about that in the previous distance formula. So do you see what's happening here? We have m here, which is or m over here, which is half. So the length of the midsegment is half the length of the non-included side, and that's what we're trying to prove. So we're done with the first part of the midsegment theorem. We just proved the first part of the midsegment theorem. This midsegment is half the length of the non-included side. And we proved that for all triangles. Or at least triangles that look like this. Let's see here. Now we're going to show that they're parallel, so we want to find the slope of FE. And I'm going to use F, as always, the first letter is 0.1. So we're using these points here. So the y value is k over 2, and we're subtracting the other y value, k over 2. And you can see already that we're going to get 0. K over 2 minus k over 2, that is just going to be 0, obviously. And then the bottom part, we don't really care what that is. We can calculate it if you really want to, but we don't really need to, so we can just put 0. So the slope of the midsegment is 0. So now we'll find the slope of AC, and show that that slope is also 0, and that'll prove that AC, the non-included side, is parallel to the midsegment. So now we're using points A and C, A the first point, so 0 minus 0 over m minus 0, which is just 0 over m, which is 0. So therefore, AC is parallel to FE. So we proved the midsegment theorem. And we can say, therefore, the midsegment theorem is true. So again, I'm not going to give you proofs with variables that are that difficult. They're going to be quite a bit easier for your homework, so don't worry about it. That was probably the hardest one you're going to see today. Let's do one that's a little easier, and then you can try the next problem. Write a coordinate proof to show that the triangle below is isosceles. So all we have to do is show that this length is equal to this length, and then we're done. So this is a much easier problem. So we're going to find the distance between A and C, using A as the first point. So we have P minus 0 squared plus W over 2 minus W squared. All right, so P minus 0 is obviously just P. And this is the part where students are going to have a lot of trouble. W over 2 minus W, it's really an easy calculation. You're just taking 1/2 and subtracting 1, so it's obviously going to be negative 1/2 W. But what you can do is write W as over 1. Remember, you can write any number that looks like a whole number. You can write it as over 1. Then you can multiply both sides of this fraction by 2 to get 2W over 2. And now we have a common denominator. So now we have W minus 2W is negative 1W. So we have negative W over 2. So it's really just basic algebra. But students really don't like having to remember basic algebra stuff. So we have negative W over 2. And we did a problem like this before. Negative W over 2 squared, that's just negative W over 2 times negative W over 2. That's just what squaring means. You're multiplying it by itself. So now we have to multiply the W's, W times W. First of all, negative times a negative is a positive. W times W is W squared, and 2 times 2 is 4. Again, this is just basic stuff, basic algebra. We may not have done problems that are quite this same variation, but it's the same concepts in pre-algebra and beginning algebra. So we have P squared plus W squared over 4. And that's the distance. We really can't do much more with that. So now we're going to find the distance between B and C, letting B be the first point. So we have P minus 0 squared plus W over 2 minus W squared. Whoops, that's not right. W over 2 minus 0 squared. So now we have P squared plus W over 2 squared. Now we can just simplify that to P squared, and like I said, W over 2 times W over 2 is just W squared over 4. So W squared over 4. And you can see that these expressions here are the same. So we proved that it's an isosceles triangle. And that's all we have to do. We just have to write our conclusion. Therefore, triangle ABC is isosceles. right, time for you to try one. We're going to write a coordinate proof to show that the quadrilateral below is a parallelogram, i.e. two pairs of parallel sides. So we have to show that this side is parallel to this side, and this side is parallel to this side. So all you really have to do is use slope. So I'm just going to write the slope formula for you. If you forgot it, it's y2 minus y1 over x2 minus x1. That's really all you have to do for this proof. So it's a very easy proof. Again, show AB is parallel to DC and BC is parallel to AD, and then you'll be done. And remember to write your conclusion statement. When you come back, we'll do it together. All right, we're back. Let's find the slope between the slope of segment AB. So I'm using A as 0.1, and we have W minus 0 over P minus 0, which is W over P. So very easy. That's the slope of AB. Now we're going to find the slope of DC and see if that is also W over P, because we want to show that AB is parallel to DC. So we have, let's see, W minus 0 over P plus L minus L. W minus 0 is W, and these L's just cancel out, and you have P, and we showed that the slopes are the same. The slope of AB and DC are the same, which means that AB is parallel to DC. So we showed that one pair of sides they're parallel. We need to show that there are two pairs of parallel sides. So now we're going to find the slope of BC. Like I said, it doesn't really matter if what pair you choose first. And that is going to be, using B as the first point, we have W minus W over P plus L minus P. And W minus W is 0, and the P's cancel out because you have one positive P and one negative P. So we just end up with L, and it's 0. So the slope of side BC is 0. So the slope of AD should also be 0. So using A as 0.1, we have 0 minus 0 over L minus 0. 0 minus 0 is obviously 0, and we have L, and then we just have 0. So those slopes are the same, which proves that those two sides, side BC and AD, are parallel to each other. So we showed in this quadrilateral that there are two pairs of parallel sides. So we can say, therefore, the quadrilateral is a parallelogram. So if you got those answers, good job. All right, so we have a few more things to do here. Bisector theorems, but bisector theorems, it's not going to be too difficult to finish this stuff out. We need to learn the perpendicular bisector theorem. And these theorems are not a huge part of the curriculum, but we need them to show other proofs, show that other proofs are true. So we're going to learn the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what in the world does that mean? Well, this green line here is the perpendicular bisector because it bisects this segment. It goes right through the middle of it. And it's a perpendicular bisector because the angle that it creates when it goes through the segment is 90 degrees. So it's a perpendicular bisector. That green line there, perpendicular bisector. Now this point is on the perpendicular bisector. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. That's it. Now it turns out the converse of that is also true. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. We're not really going to use the converse too much in this class today. So you might be thinking, well, what in the world does all that mean? Well, let's just do some practice problems and you're going to see exactly what it means. So this point is on the perpendicular bisector. How do I know it's a perpendicular bisector? Because these lengths are equal and this is 90 degrees. So we know this point is on the perpendicular bisector, but if that point is on the perpendicular bisector, and by the way, if you didn't get screenshots, go ahead and get screenshots of these. If that point is on the perpendicular bisector, that means it's equidistant from the endpoint. So this length must be equal to this length. Very easy. So x must be 3. So these are really, really easy theorems. All right, so now we have another perpendicular bisector because this length is equal to this length, which means that it's bisected. This line is bisecting the segment, and it's also 90 degrees. So because this point is on the perpendicular bisector, that means this length must be equal to this length. It's equidistant from the endpoints, from these endpoints. This point is equidistant from those endpoints. So that means that 2x plus 1 is equal to 3x minus 4. And we just subtract 2x from both sides and add 4 to both sides, and we get x is equal to 5. But we're not done because we don't want x. We want BC. So BC is equal to 3 times 5 minus 4, which is 11. And that is the answer for that one. All right. So let's try one more of these before you try one on your own. Find AC. So we know that this line is bisecting. This line here is bisecting this segment because these lengths are the same. So it's a segment bisector, but the problem is it's not a perpendicular bisector because we don't have the angle here. Whoops. We don't have this angle. We don't know it's 90 degrees. So we don't know that this is a perpendicular bisector. I mean, the line could be slightly off this way, so we don't know that this point is on the perpendicular bisector. And so we can't say, well, BC is 3.6, therefore AC must also be 3.6. We can't say that because, again, we don't have enough information. So we can just say, not enough information. It looks like it's on the perpendicular bisector, but you can't just assume that it is. It might be slightly off. That is the answer to that one. All right, so hopefully you've got enough there. You can take screenshots of the problems that we just did. That might help you. But you need to try these next problems on your own. Try number 27, and when you come back, we'll do it together. All right, we're back. These lengths are equal, meaning that that line bisects this segment. We also know that this angle is 90. In the previous problem, we didn't know that. So because the line bisects the segment, and because it's a perpendicular bisector, remember 90 means perpendicular, that means that this point here on the perpendicular bisector is equidistant from the endpoints, meaning 50 must be equal to 5x. Divide both sides by 5 and you get x is equal to 10. So if you got 10, good job. If you didn't get 10, that's okay. Just figure out what you did wrong and go back and fix your mistake. All right, let's try the next problem. Try number 28, and when you come back, we'll do it together. All right, we're back. So this is this line is perpendicular to this segment. The problem is we don't know it bisects the segment, you see, because we don't know that this length is equal to this length. So we don't know that this point is actually on the perpendicular bisector. We know it's on a perpendicular line, but we don't know that it's a perpendicular bisector. So there's not enough information. We can't tell that this point is equidistant from the endpoints. So if you got tricked by that, that's okay. Those are the two ways to tell that we don't have enough information, pretty much, that we're either going to be lacking the 90-degree angle, or we're going to be we don't know that those two lengths are equal, meaning it's a bisector. Try number 29, and when you come back, we'll do it together. All right, we're back. Now we know that it's a bisector because this length is equal to this length. So we know that that line with the arrows bisects AB. So bisects AB. And we also know that it's a perpendicular bisector because that angle is 90. So then we know that this point, which is on the perpendicular bisector, is equidistant from the two endpoints of this segment. So that means that 3x plus 10 must be equal to 22 minus x. We're going to add x to both sides, and we get 4x plus 10 equals 22. And subtract 10 from both sides, and we get 4x is equal to 12. And divide both sides by 4, and we get x is equal to 3. And we're not looking for x. We're looking for AC. So AC is equal to 3 times x, which we know is 3, plus 10, which equals 19. And that is the answer. So if you got 19 for AC, good job. Remember, you're looking for AC. You're not looking for x. All right, so that is the perpendicular bisector theorem. We just have one more thing to do today, and then we'll be done. This is another theorem that is really not a huge part of the geometry curriculum, but it is something that we're going to need for other proofs. So this is the angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the rays of the angle. What in the world does that mean? Well, this is an angle bisector. Why is that an angle bisector? Well, because if you look at this angle here, this ray goes right in through the middle of it, which means that this angle here is equal to this angle. It cuts it in half. It's just like a segment bisector, but in this case it's an angle bisector. So if this point is on that angle bisector, then it's equidistant from the rays of the angle, meaning this length is equal to this length. And the reason we have a 90 degree angle here is because the shortest distance is going to be a length that is perpendicular. That's kind of something that just falls through the cracks of the curriculum, but there's some sort of a theorem that we need to show that the shortest distance between these rays is going to be a segment that's perpendicular. Now it turns out that the converse of that is also true. If a point is on the interior of an angle, meaning if the point is somewhere over here, not outside on the exterior, but in the interior of an angle, if this point is on the interior of the angle and it's equidistant from the rays, then it's on the bisector of the angle. All right, so this one is a little more complicated than the previous one, but still not too bad. So if you don't understand what all that stuff means, that's okay. Let's do some problems together. Find x if possible. So this is an angle bisector. I know that because this angle here, this arc, is the same as this arc. So I know it's an angle bisector. And because it's an angle bisector, and because this point is on the angle bisector, that means it must be equidistant from the rays. So that means x plus 3 must be equal to 19. Therefore, x must be equal to 16. And that's the answer. So not too bad. We used the Angle Bisector Theorem. We didn't use the converse theorem yet, but we're going to use the converse theorem in the next problem. In this problem, we know that the point is equidistant. This point on this ray is equidistant from the rays of the angle, these two rays. And so because it's equidistant, that means that this must be the angle bisector, which means that these two angles must be equal. So that means that x must be equal to 18 degrees, and you're done. So it's pretty easy on that one. Let's try 32 together. A couple more of these so you can get the hang of this. So we know that this is an angle bisector because this arc here, this angle is equal to this angle. So therefore, by the angle bisector theorem, this point must be equidistant from the endpoints, and because we have 90-degree angles, we know that that's the shortest distance. So that's the distance between the ray and the point. So we know 2x minus 3 must be equal to x plus 5. Subtract x from both sides. Add 3 to both sides, and x is equal to 8. Now be aware that I didn't mention, you must have these 90-degree angles. If you don't have these 90-degree angles, then it's not necessarily the shortest distance from the point to the rays. So just be aware of that. Again, that's something that kind of falls through the cracks of the geometry curriculum. So on number 33, we don't know that these lengths are equal. We do know that that these are 90 degrees, 90-degree angles. We don't know that this is the angle bisector because we know that this angle is 31, but we don't know that this angle is 31. So there's really not enough information to find x. So that is our answer, not enough information. So why don't you try number 34? And if you haven't got a screenshot of those theorems, go ahead and get that screenshot. And try 34. When you come back, we'll do it together. All right, we're back. We have 90-degree angles, which means that these lengths are the shortest distance from the rays to the point. And we also know that these lengths are equidistant, or excuse me, that those lengths are the same, which means the point is equidistant. So therefore, by the converse of the angle bisector theorem, these angles must be equal because the converse says that this ray is an angle bisector. So that means that 43 must be equal to 6x minus 5. Add 5 to both sides. Divide both sides by 6, and we get 8. So x is equal to 8. So if you got 8, good job. All right, go ahead and try number 35, and when you come back, we'll do it together. All right, we're back. We're going to use the converse of the angle bisector theorem again, because we know these lengths are equal, and we know that they're the shortest distance from the rays because of the 90-degree angles. And so therefore this ray is an angle bisector, which means that this angle must be equal to this angle. So 2x must be equal to 44. Divide both sides by 2, and we get 22. And if you got 22, good job. All right, on to number 36. Go ahead and try number 36. And when you come back, we'll do it together. All right, we're back. So I know that this ray is an angle bisector because these two angles are equal. So by the angle bisector theorem, this point, which is on the angle bisector, must be equidistant from the rays. So that means that x must be equal to 8. And there you go. So if you got 8 for that one, good job. Actually, we forgot to write centimeters. Probably should write centimeters there. All right, try number 37, and when you come back, we'll do it together. All right, we're back. I know that this point is on the angle bisector. I know this ray is the angle bisector because these angles are equal, and these angles are 90, meaning that those are the shortest lengths from the rays to the point. So by the angle bisector theorem, that means that the point is equidistant from the rays, so 2x is equal to negative 3x plus 10. Add 3x to both sides, we get 5x is equal to 10. Divide both sides by 5, and we get x is equal to 2. Now, if you're having trouble with this algebra, then you need to go back to my pre-algebra course or my beginning algebra course. Actually, it's going to be in my pre-algebra course probably. So if you got x, or if you got 2 for x, good job. Go ahead and try number 38, and when you come back, we'll do it together. All right, we're back. We're using the converse now, the converse of the angle bisector theorem, because we know that these lengths are equal, and the 90-degree angles tells us that it's this is the shortest distance between the ray and the point. So by the converse, that means that this ray must be an angle bisector. So that means that these angles are equal. So 4x plus 10 must be equal to 3x plus 20. Subtract 3x from both sides. And subtract 10 from both sides, and we see x is equal to 10. So if you got 10, good job. All right, we have, looks like one more problem for this entire class. Go ahead and try number 39, and when you come back, we'll do it together. 39's got a little trick there, so be careful. Go ahead and attempt that. When you come back, we'll do it together. All right, we're back. Now, we know that this length is equal to this length, but that really doesn't tell us anything. We need to know that this length is equal to this length. Then we could use the converse of the angle bisector theorem. But we just don't have that information. And we don't know that this is an angle bisector because we don't have any angles here. And we don't even know that that these angles are 90, so we don't even know if those are the shortest. So there's really we're completely lacking information needed to use the converse of the angle bisector theorem or the angle bisector theorem itself. So we just say not enough information. And that was the class today. So we learned coordinate proofs with variables and with regular numbers, and we learned the Midsegment Theorem. Now, if you want to get screenshots of all the work we did today to help you with your homework and to study for tests, go ahead and do that now. All right, now let's look at the homework. Get a screenshot of these first 2 pages and a screenshot of the 3rd and 4th pages. the 5th and 6th pages. And don't go before you get the answers for numbers 1 through 6. Get a screenshot of that. And also, we want the answers for numbers 11 through 14. So answers for 11 through 14 are here. Whoops, sorry about that. So we have 11 through 14. And we also need answers for 22 through 23. So be sure to do that homework completely and correctly and neatly. And make sure that your homework is in your binder in the proper chronological order. And remember, if you don't do homework, you'll learn absolutely nothing in this entire course. So get that homework done, and I'll see you in the next class.